You have to estimate a lot of it. Try to figure out what the central code parts are, routines and classes, and modules in general, and whether there are isolated code regions, which is an excellent candidate for that code. This information about central code parts and candidates for that code can be derived from relationship graphs, inclusion graphs, that's binary object import, like PE import, or includes use and include, and Java import and class usage. That's nasty, actually. I thought I could just go ahead and read all the import statements in the Java file and then I'm done, but it's a bit trickier. There's a whole host of other relationship graphs, and I haven't implemented all of them. I did inclusion graphs. I didn't do any of these up to now. I'll stop that. Control flow graphs, I did. Inheritance graphs, up to now, no, but it's readily available in Javadoc, I believe. You get these pretty inheritance graphs if you turn on some option or other. Membership graphs are also interesting, but I don't believe that Javadoc or Doc6 can do that right now. Function call graphs, haven't done that because of lack of time. Data flow graphs are a bit trickier if you work with source code, especially if you work with C source code. Control dependency graph and data dependency graphs are the same issue as data flow graphs, plus they're rather esoteric. I should probably explain a bit of what all these graphs are about. Inheritance graph, that's clear, so if you have a class hierarchy and one class inherits from the other, so that's clear. Membership graphs, if you don't extend code by inheriting, but by just including an instance of the class in question. Function call graphs should be obvious. So the nodes are functions, and two nodes have an edge if one function calls the other. Control flow graphs are usually done as basic block graphs, so you have alternate decisions, if then else, and split up. We're going to see them later, so I don't have to elaborate here. Data flow graphs, just are also based on basic block graphs, and then you just follow a certain variable or a certain value through the basic block graph and see how it gets manipulated and where it gets manipulated. Control dependency graphs and data dependency graphs are too esoteric to elaborate on right now. If somebody is interested in compiler design anyway, read Steve Muchnick, Advanced Compiler Design and Implementation. It's explained beautifully there. So, I don't know, graph theory background? Not really. Components is a really simple concept from graph theory. You have a heap of nodes in some place and a heap of nodes on the other, and one heap is connected among one another, but they're not connected, interconnected. So you have two separate heaps of nodes, and the two separate heaps of nodes are called components. And if you find in the named graphs, inclusion graphs, or control flow graphs, or call graphs, more than one component, this may hint that there's dead or unused code in this code, but it need not necessarily be, especially in C, where you have all sorts of funky function pointers, which are not easily captured when you generate these graphs. So if you want to know how complex code is, the obvious measure is lines of code. That's not really very useful if you want to use it as an absolute measure. So how complex is a file with 100,000 lines of code. That's not a very useful statement, but if you have a number of files and compare them and say, okay, there's one file which only has 10 lines of code, I probably don't have to put much time in there, and there's probably not much interesting functionality in there. Then you have the infamous relationship graphs, which I mentioned earlier, inclusion graphs, control flow graphs. From their structure and complexity, you can usually always also say something about the code complexity. If it's very intricate graphs, then you have high code complexity, which is not necessarily saying that the code is very complicated or that the functionality is very complicated to achieve, but it says that possibly the developer has smoked a bit too much and didn't do proper software engineering, which makes it harder for you to audit the code. Because the more structure there is in the code, the easier it gets to find your way around it. Estimating code quality. Comments are somewhat useful in that, but not. There's not a linear relation between amount of comments and code quality. So there can be tons of comments in code saying nothing. That's the paper line approach. If somebody is paid by the lines that they write, they tend to draw fancy function headers, repeating all the arguments and drawing fancy ASCII art around it. So that shows up as lots of comments, but it's not really useful. So what you look at is the frequency and distribution and extensiveness and type, and you can usually just see certain patterns. So if you, I have a picture after that, I'm going to show you them. Then there's distribution of certain keywords in a file, typical candidates, bug, to do, fix me. And if you graph this really quickly, the blue stuff is comments, the gray stuff is code, the red stuff are occurrences of bug, fix me, hack, to do. This is not such a good piece of code, it's very short, but has a lot of these occurrences of fix me and hack. And in here, one pixels, one line of source code. And the squares are separate functions. And a very typical pattern in this paper line code is that you have one function, so one gray box, and then above it a huge blue box, and it repeats over and over. And if they're rather uniform, the blue boxes, that's a good indicator that the comment is going to be useless, because the programmer just wants to spend time writing comments. So that's one instance where you have one picture and can see almost immediately, give an estimation of what the code is going to be like, or identify typical instance of strange code. Because usually, I don't know if you follow me there, but usually if someone spends their time painting fancy function headers, comments, I don't have much confidence in their coding skills immediately. Another interesting topic is code history. Code history can be very revealing. It's another instance where you have one picture and you can immediately give an estimate of how good the code is going to be. And it's also nice that data on code history is in a lot of projects readily accessible, so via CDS or Subversion, or Rational is more often used in commercial settings. And there's a nice heuristic measure for code quality there, because all code, few changes is usually bad. It means it was written long ago and somebody forgot about it and never cared about it anymore. And it was probably not really heavily used, so that's probably a part of the code that wasn't often reached. But that's not to say that it's never going to be reached. So if you can find old code with few changes and then make the software enter these code parts, you're likely to find interesting bugs. Or the new code that has seen massive changes is also not necessarily bad, but very suspicious, because with massive changes usually also come lots of bugs. If you see old code with many incremental changes over time, that's good. That means that it has been maintained continually and it has been in use and people have found bugs in it and removed bugs from it. And in new code, there's not really much you can say. But it's also just an estimate, but it's so nice because you can see it at a glance. So I haven't actually implemented that feature, that's just a mock-up. A is old code, so the funky bubbles there are the code changes, and this is timeline, and each string is one piece of code. So the code in A is rather old and has seen quite a few incremental changes over time, so that's less likely to be riddled with holes. Code B is compared to that relatively new and has seen a lot of massive changes. Code C is very old, but somebody obviously forgot about it about here. And D is very new, you can say much about it. And if I had to choose, if somebody said, okay, you have time to audit exactly one of these pieces of code, I'd go for either C or B, because that's most likely to contain bugs. A pointy video, while I was preparing this talk, I also noticed that there's a revision history viewer available from FreshMe, 2 years old. I couldn't get it to run, it just crashed on me repeatedly, and I didn't really have the nerve to figure out why. It's an Eclipse plugin, it sort of, well, stay with me, sort of does what I was talking about. Grabs the code pieces over time and changes as little bits. So if it runs, it's probably cool. Experiment 1, spatial metaphors for code. This is all highly experimental. I don't have any user interface lab behind me to back this up. This is all just speculations from my daily practice experience when auditing code. Okay, code is complex. Unless you have Hello World, which is not very interesting. Not that you can introduce bugs in Hello World, but usually it's not Hello World you get to look at. So you have lots and lots of complex abstract structures. Introducing a spatial metaverse for source code might help you to free up some cognitive resources and make relations among the different code parts apparent, and provide a sense of orientation. When I'm faced with a repository of new code, there's always this sense of being completely lost. I have no idea where I am, I have no idea where to start. And this only gets better after a week or so, but relies heavily on my explicitly building in my head representations of this code. And I was thinking about whether you could make this explicit. So the basic idea is to convert abstract properties of source code into spatial properties. And suitable features are obviously size and relationships between code parts, and occurrences of features like search terms and references to code entities. And you can choose whether you want to treat the representations as general graphs, so more if you come from a more graph theoretical background, or just as maps, so you draw maps and try to chart your ways around in these code maps. Most basic thing is to graph the directory hierarchy in size. So that's one small code repository where you have the root directory, and the leaves are code files, so files containing source code, and their size is according to the size on the disk. So not really how much code is in there, but just the size on the disk. So next thing to do is then embed code features into this fancy map, and the obvious thing to do is choose term occurrences. So I selected for you to play with. Oh wait, give me long. HITBSecConf code, and it's interesting to see it light up if you search for suspicious terms. Like I tried searching for string copy. So HITBSecConf is obviously a bit larger, 1,000 files, and you can see that there are not incredibly many occurrences of string copy in this code, but there are some. The red ones, the red ones occur contain string copy, calls to string copy. Which is not such a good thing for such an exposed library. And another fun thing to look for is always hack. So what do we all do if we have to implement some part in code and are too lazy to think about how to do it properly at that moment? We just write a comment and put something in there like hack. This is also not so entertaining. I mean, I haven't looked into many of them to see what the heck was at that particular piece of code, but it's just to illustrate that you have one picture and can get a sense of, oh, there's possibly some problems there. I should look into this file and down there possibly to see whether there's actually some problem. And a request for search terms.
Fix me.
Yeah, that's Eclipse. It's slow, still. I don't really know which version I have. I believe it's a version I leaked 3 months ago, so pretty recent. So if any of you is bored tonight, you can have a look at HITBSecConf. So that's one of the examples where pretty features can help you find your way around the source code and see what you're going to look at. That's just in case the demo wouldn't work. I don't trust computers. So that's that, highlighting search terms in source code. Another thing you can do is chart path in these maps, which can be really useful in code and data flow graphs or call graphs. So track a certain property across the code. And it's useful in any kind of tracing, be it the access to certain variables or the access to user input, or also a long-term period log acquisition and release. it's bad style to do the locking not in the place where you're actually accessing the shared variables, but somewhere else. But you see it a lot of time, and it's not always bugged because sometimes some of the calling, all of the calling functions acquire the lock and release it properly, but sometimes they don't. So that's one point where the code quality is bad, although there are no real bugs in there. If you change anything, you're likely to introduce strange bugs. Implementation notes on what you saw that one thing at least runs, and the work I'm currently doing is based on Eclipse and Y files. If somebody has seen Thal's work and is finding it at least visually similar to what I'm doing, that's because we use the same graph library. And it's implemented as Eclipse plugins and uses the IDE and the Java development tools and the C development tools, which are actually quite cool, although Java's a bit annoying. So why I use Eclipse is that the plugin architecture is very convenient, and it already has a lot of the stuff that I'm going to build on. I tried using OpenGrok first, but they hard-coded HTML output into the Lexer, so I'm not going to use that. So control flow graphs. We all know control flow graphs, possibly because of Thal. They have been widely used for 2 or 3 decades in computer science, in compiler design and implementation, and in debugging and reverse engineering. And compiler design and reverse engineering use control flow graphs on machine level language instructions, so IL32 or whatever architecture you pick, be they virtual or real. So what actually makes control flow graphs useful in reverse engineering? They're pretty much taken for granted where I come from, but what actually makes them useful is that there's information implicitly contained in the instruction sequences, so you have just lots and lots of listings, and this information is made explicit if you build basic block graphs and depict the control flow within these graphs. It's presented in a way that's really easy to handle by the human visual system, because humans are rather good at seeing relationships that are depicted by connections between entities, and thus it helps to reduce the cognitive load. So you have to use all the cognitive resources you can get in reverse engineering, because it's such a low level of abstraction. So any help in doing that is appreciated. How control flow graphs do that is by visually displaying code as lines that connect dots. So the dots are pieces of code, and the lines are the flow of the possible flows of the control. And there's even research on that. So the scientists on my side, Colin Wares and Excellent Treat information visualization. If you want to know more about that, it's really the easiest way for humans to recognize relationships. Of course, there are opportunities to get even more of the human visual system, which is millions of years old, so we should use it. Animation. We already have the word flow in control flow graphs, so make just some sort of blue stuff flow along the lines. I've actually seen that. I'm not sure where. I'm not sure whether Vietnamese got that. And then you get again a spatial method for sequences of instructions. So they are arranged in space and in a way that puts related code parts closer together. So once again have a sense of orientation within the code. So in theory, the cognitive effect should be similar in source code reading. There's no reason why that should be limited to machine level language code. But on the other hand, you have a higher abstraction level in source code. So if you have the source code, you want to use it. And there's another reason source flow graphs are much cooler if you have them because they're less complex than basic machine level language flow graphs, which is in here. The red region is source code basic block graphs, and the green stuff is the corresponding machine level language flow graphs. Nice to look at. So the logical step is to try and provide control flow graphs that incorporate the available source code. Something that I've first tried a year ago, and did the really entertaining thing of thinking I could just do it in Perl in an afternoon, which meant I ended up trying to write an ad hoc parser for C. I saw stars at the end of the night and didn't get much farther, so I decided to just let other people do the parsing. And this is what a hello world might look like then. So that's actually generated from code. Yeah, speaks for itself. It's not much to elaborate here. Where's my pointer? Anyway. So building source code flow graphs is not really rocket science, but it's not straightforward either. The general method is that you have to get a mapping of the source code blocks, IP lines, to the machine level language that it translates to, and then construct the low level basic blocks. So you do all the things you do in machine level language basic block graph construction, plus then you take the machine level language basic block graph and the mapping of source code blocks to machine level language code blocks, and project the basic blocks onto source code using that mapping. As a result, you have the source code flow graph and the mapping from low level flow graph to the source flow graph, which is not really useful, but I like to maintain it for defensive purposes. Whether my pretty picture will. Anyway. There. There was supposed to be a pretty picture there. I'm confused. The mapping of source code blocks to low-level language code blocks was what I initially tried to do ad hoc. Bad idea. So you, option 1, build a compiler. That's what I tried to do. Not so good. Option 2, use existing tools, compilers or debuggers. And one option is using the Visual Studio compilers with or without managed code extensions, but it's especially easy if you use the managed code extensions because there's a compiler switch that outputs .cod files, which is exactly what we need. It's just a line of source code and then the statements it translates to before optimization. So everything you do, you get before optimization, otherwise it's going to become difficult or impossible to construct the mapping between machine level language and source code statements. Other compilers and configurations are also possible, but I haven't looked into that yet. And here, the theory, all the information you need should also be in the assemblies of the PDB files, but yeah, another time. If somebody feels like coding, no, probably not. What you could also use is GCC. The data should also be available in the debugging information if you compile the code with the -G switch. And the quick and dirty Perl magic approach I tried at first failed because I tried using GDB and just ripping the information I needed out of that, but that failed because it's GDB. It forgot symbols and other annoying stuff. Yeah, what I did in my proof of concept that also generated the pictures I showed you works with C and C++ code in Microsoft's Visual Studio C and C++ compiler, either with or without managed code extensions. So if you compile it with managed code extensions, you're just going to get CIL code, and if you compile it without for IR32, then you get obviously IR32 instructions. It gives the most useful results with well-styled code, so one statement per line, no heavy use of side effects like if statements with multiple function calls and comparisons, because then you have one line which translates to a lot of source code and a lot of different basic blocks, but it's all going to end up in one line of source code. So this is my basic level of granularity, and I don't think it makes much sense to split up individual lines of source code. Yeah, the graph handling and editing and displaying is again quite fast library. So what I have to work with is the source code control flow graph itself. The low-level code control flow graph, I get this for free, basically, but it's not that much use except for debugging. And then a mapping from the low-level basic blocks to the source code basic blocks. There's not really good. Green one is, I believe it's IR32 instructions, and the yellow one is the original source code. And what is already apparent from this picture is that the mapping is not one-to-one but end-to-end. So one basic block graph in machine level language code can contribute to several basic blocks in the source code and vice versa. And that large block there is there because there's lots of statements in the function prologue which you don't really see in the source code ever. So this is just the groundwork, because all the control flow and data flow analysis can be implemented on low-level flow graphs, and because I maintain the low-level flow graph and the mapping, it can then be mapped back to the source level flow graph. But I haven't looked into that yet. Maybe sometime in the future. And just to be complete, there's some related work in the academic world out there. What they do a lot of software visualization, but it's very UML heavy, so they try to extract UML diagrams from source code and then display the UML diagrams. And the keywords to look for here, if you're interested, is Bauhaus, which is a German project, and WCRE, which is the World Conference on Reverse Engineering. There's actually such a thing in the academic world, but it's very boring what we do. And then there's a conference on software visualization, which is the International Conference on Software Visualization, SOFTIS, held by the ACM annually. So, that's it from my side. Yes?
Can you show us a sample of the COT files you get from Microsoft? Can you show us a sample of the COT files? Do you have that?
I'm not sure. I'd have to search and then I'd have to show you all my disk contents, and then not really wild for that. So, if you want to see that, we can do that later after the talk.
Any other questions? Any other questions?
get out 7 minutes early.
Thank you very much, Lisa. With that interesting presentation, ladies and gentlemen, we conclude day 1 of Hack in the Box Security Conference. We'll see you all tomorrow, bright and early in the morning at 9 o'clock for the first presentation for both tracks. See you then. Have a good evening. Bye-bye.